So during my PhD, I worked on aftershock sequences. And so a recurring theme throughout my research career has been understanding the role of complexity in fault geometry and how that affects seismicity. So when we first come up with a model of a fault, we tend to think of a plane because that's the simplest representation. But in reality, if you look at faults on a map, you see a lot of geometrical complexity, you see a lot of different parallel structure, you see what actually looks like a fractal geometry, and it is to first order. And so clearly a representation in which you have a straight line or a plane is not sufficient. So I've been working on including some of this geometrical complexity into models of aftershocks and later also foreshocks to understand how does seismicity look like when you include all this complexity. And during my PhD, for example, we found that I was working on physical models of aftershock sequences. So the idea in these models is that you have a large earthquake, say magnitude 5, 6, 7 or so, and this earthquake produces stresses around its neighborhood. And so other faults will then be triggered, and then you will have an aftershock sequence. And what we found is that when you include all this geometrical complexity in the physical model, you get a much better result, you get a much better forecast for the evolution of the sequence in space and time. More recently, in the last year, I've been looking again at the connection between the geometry of a fault and the seismic sequences. And this time, instead of looking at aftershocks, which are the earthquakes after a large earthquake, I was looking at foreshocks, earthquakes that sometimes take place before a destructive earthquake. And so what we found is that, once again, the inclusion of geometrical complexity has a really important effect in the behavior of the fault. And specifically, when you look at the beginning of a large earthquake on a planar fault, you have a very localized acceleration. So there is some precursory signal before the earthquake itself, but it's very small, it's very fast, and it happens over maybe a region of 1 meter or so, which would be virtually impossible to detect. On the other hand, when you include this additional geometrical complexity and you represent the fault not only as a planar feature, but you include some roughness, you get a much more extended precursory signal. It has a much wider extent in space, it lasts for longer, and it also includes several smaller earthquakes, which are very similar to the foreshocks we sometimes see in nature. And we could also match some of the typical features that are seen during foreshock sequences, including migration and also an increase in the number of events with time. So this is an encouraging result, even though we definitely need to think more about which cases in nature are well described by this model. Why is it that in nature we don't always see these precursory signals? And what are the physical conditions that really determine them? But at least we have some encouraging results in that we've been able to match some first-order features and really understand the role of this complex geometry on the sequence.